Hi, my name is George Diamond again. We are still in we're still in section 4.4 of our textbook here. At my school we use the Larson text, and this is 4.4. In this one section we look at the first fundamental theorem of calculus and the second fundamental theorem of calculus. Now we've done several videos looking at this section in our textbook. We've looked at the first fundamental theorem of calculus, area under a curve. We did a video on the average value theorem, where we looked at the average value theorem. We looked at the mean value theorem. We did a video involving an integral as a function of x. Right, so that was our last video. Now in this video we're going to look at the second fundamental theorem of calculus. So we're finally to the second fundamental theorem of calculus. Now we're still going to do one more video on this particular section. We need to look at some applications. We'll do some accumulation functions. We're going to look at the several applications involving the fundamental theorem of calculus. But let's go and get straight to it. Let's go and take a look at the second fundamental theorem of calculus. Now, this is what it says. It says if f is continuous on an open interval containing a, then for every x in the interval, all right, the derivative of the integral from a to x of f of t dt is equal to f of x. So equals f of x, little f of x. So the derivative with respect to x of the function from a to x of f of t dt is equal to f of x. Now, several implications of the fundamental theorem of calculus, and this is one of them. I got several of them here. Let's take a look at some of the implications of what this fundamental theorem of calculus implies. Okay, the first implication I want you to remember, so what this implies is that every continuous function, f, is the derivative of some other function. So every continuous function is the derivative of some other function. So that's one implication, or the first implication here I want to mention about the fundamental theorem of calculus. So every continuous function is going to be the derivative of some other function. Now the second implication, let's see if I can get this off. There we go. Now the second implication I want to mention says that it indicates that every continuous function has an antiderivative. So every function is going to be the derivative of some other function. Well, every continuous function has an antiderivative. Now sometimes it may be kind of tough to get the antiderivative, but every continuous function has an antiderivative. So that's one of the implications of the fundamental theorem of calculus. Now one more implication. I'm going to pull this next one up here. I can do it. There we go. So one more implication that the fundamental theorem of calculus implies. And that's that differentiation and integration are inverses of each other. So they're inverse operations. Just like addition and subtraction are inverses, multiplication and division are inverses. All right, so this is the third implication I want you to be aware of involving the fundamental theorem of calculus. All right, so think about this. The derivative of this integral from a to x is equal to f of x. All right, so let's do a little problem here. Okay, let's see if we can kind of demonstrate this with an actual function. So we're going to pull this here down, and we're going to do several derivatives. All right, so let's start off with the first one. Now the first one we'll do it the long way. So let me erase this. All right, so let's see. Let me erase this. All right. So let's see if we can find the derivative. So the derivative. All right, now let's try this here. We'll find the derivative of, so d over dx of, let's see, let's do the integral from a to x. And this time we'll do from pi to x. So we need a constant for our lower bound, so from pi to x of cosine t dt. Right, so we're going to take the definite integral from pi to x, and then we're going to take the derivative after that. So Now there's actually a very short, easy way to take this type of derivative, or derivative of this type of function. So from pi to x of cosine t dt. So let's start off, let's do the integral part first. Now in our last video, we looked at evaluating this type of definite integral in which the upper bound was a variable. So let's go and do the integral part first. So to get us started, now then at the end we'll take the derivative of what's left. So to get us started, let's say, let's get our antiderivative first. So the antiderivative of cosine t would be sine t from pi to x. All right, so let's find our antiderivative. Now to evaluate our antiderivative, we got to substitute the upper bound minus the lower bound now. So if we substitute the upper bound in, will give us sine x minus sine pi. All right, now, so we end up with what? Sine x minus, now sine pi is 0, so sine x minus 0 or just sine x. Okay, now this is the integral. All right, so this expression right here, sine x, would represent the area between the curve and the x-axis from pi to any number. So from pi to any number. Now, let's do the derivative part of the second fundamental theorem of calculus. Okay, let's take the derivative of sine x. Now, the derivative of sine x is, if you remember, is cosine x. There you go. So the derivative from pi to x of cosine t dt is actually cosine x. So with this type of problem, I kind of did this kind of the long way. Okay, this type of problem can be done very quickly, okay, using the chain rule. So basically what we could have done, so we end up with cosine x was our derivative, right? So we take the derivative of your integral, okay, we get cosine x. So we started with cosine. So an easier, even faster way to do this type of integral is basically the chain rule. So basically the chain rule. So a fast way to find the derivative of this integral function is to take the exponent, substitute in for t, so it'd be cosine of x times the derivative of x. So this is the chain rule. All right, so take your upper bound, right, substitute it into your function for t or whatever variable it is you're integrating to describe in terms of, okay, times the derivative of the upper bound. Now the derivative of x is 1, so you have cosine x times 1 or cosine x. There's the derivative. All right, so now you can do the integral first and then take the derivative of what you get, but you know that's a lot of extra work, a lot more than what we need to do. So this type of derivative we can do very quickly. You just have to take the upper bound, substitute in for t or into your integrand times the derivative of the upper bound. So it's actually the chain rule that you're using to get your derivative. Now let's do a couple examples. This is our first one. So let's do this one here. This is just a little illustration. Let's do several examples. Let's start off number 1. Okay, we're going to do these quickly, right? Because these don't take long to do, right? So to find the derivative. So let's take this function right here. F of x is equal to the integral from 0 to x of the radical, okay, t squared plus 2 dt. Right, so let's try the derivative. Now, as you get your derivative, all we got to do now, remember now, we're going to do this. We're going to use a shortcut here. This is the chain rule. Okay, all we have to do is take the upper bound, substitute in for t, and the derivative is, so f prime x is going to be equal to the square root of x squared plus 2 times the derivative of x. Now the derivative of x is 1, so we can say the derivative here with respect to x is equal to x squared plus 2. So basically you just have to take that upper bound and substitute it in. So like I said, integration and differentiation are inverses of each other. So the derivative kind of think of it as the derivative removing the integral. They kind of cancel each other out and leaving us with your function in terms of x. Okay, let's try. So problem number 1, let's try another one. Let's try this one here. So number 2. Okay, that was a radical function. Let's try a fraction. So do f of x is equal to, okay, 1 over, or the integral from 2 to x. 1 over 1 plus t squared. So 1 plus t squared dt. Now, let me point out, when you're taking the derivative of this function now, so when you're taking the derivative, it doesn't matter what the constant is. So it can be 2, it could be 200. It don't matter what this constant is, because if you remember when you take the derivative there, it'll end up all in terms of x. So to take the derivative, all we do is substitute the x value in for t would be 1 over 1 plus x squared times the derivative of x. Now the derivative of x is 1, so here's your derivative. All right, so here's our derivative. Okay, let's try another one. Now, I'm sure you're thinking, that this can't be this easy. Well, it's actually pretty easy to take these derivatives of this type of function in which the upper bound is a variable. So let's try a trig function. Let's do this here. Okay, number 3. And this time let's do f of x is equal to, so f of x is equal to the integral from pi to x cosine t dt. So let's try this problem right here. Okay, so let's see now. Once again, as we find our derivative, the derivative of f of x, the derivative function will be equal to cosine x times the derivative of x. Now, once again, the derivative of x is 1, so there's our derivative. So the derivative of the integral from pi to x is cosine x. All right. Now, let's try almost the same problem. Now, we're going to change it just a little bit. Okay, what about the number 4? So this will be another problem. So number 4. Okay, let's try the function f of x equals from pi to x to the 3rd power now. So x to the 3rd power. Okay, let's try this derivative. Now remember that you're actually using the chain rule. So as you all we got to do is take our upper bound, we'll substitute it in for t, and we end up with cosine x to the 3rd power times the derivative of x cubed. Now remember, take the derivative, you multiply, bring the 3 down, subtract 1 from your exponent. This will be cosine x cubed times 3x squared, or 3x squared times cosine x to the 3rd power. So this is our derivative now. So this is our derivative. So if your upper bound is a variable expression, some variable expression other than x, once again, as you take your derivative, it's the chain rule kind of. So substitute the x to the 3rd power in times the derivative of x to the 3rd, and that's the derivative. All right, let's try, now I think we can do one more problem. So like I said, these go pretty fast. Okay, let's try this problem right here. Okay, this time, let's try a problem in which the upper bound and the lower bound are both variables. So what if we have this problem right here? Let's say we got 5x, this is number 5. Let's say we got g of x is equal to the integral from x to x cubed sine t dt. Well, actually, we change it to make it a little bit more interesting. We'll do, instead of sine t, let's do sine of t squared dt. Okay, let's try this integral here. Now remember now, to evaluate this type of integral, the lower bound pretty much needs to be a constant. So with this type of problem, in which the upper bound and the lower bound are both variable expressions, okay, we're going to have to break this apart using 0. So we have to rewrite this. So to evaluate, to take this derivative now, we're going to have to rewrite this as, let's say g of x is equal to, we're going to do the integral from x to 0. Right, so we'll break this apart. Okay, the sine t squared dt, okay, plus the integral from 0 to x cubed sine t squared dt. Right, so we've got to break this apart. I'm going to use 0 here from x to 0, and then 0 to x to the 3rd power. Right. Now, let's see. Now, first thing I notice now is you look at this first integral. In order to take the derivative, we need the upper bound to be our variable. So the x has to be up here, the 0 needs to be down here. So remember now, in a previous video was that we can switch the upper and lower bounds, but you got to take the opposite of your integral. So this is the same thing as the opposite of 0 to x sine t squared dt plus the integral from 0 to x cubed. So sine t squared dt. All right. Again, we broke it apart. We've rewritten the first integral so that the upper bound now is our variable. The lower bound is our constant. All right? So you get your variable on top, your constant on the bottom for our lower limit. So we're ready to find our derivative now. Let's take the derivative of this first one here. Remember now, to take your derivative, we're using the chain rule. And this first one, just substitute the x in for t. So this would be so once again, g prime x. So the derivative of g of x is going to be equal to the negative sine x squared plus. So once again, you have to substitute the x in. Times the derivative of x would be just negative sine x squared. Okay, plus. Now this time you got to take the x to the third, substitute in for t. And this time we're going to have sine. Now sine is already squared, so it'll be sine of x cubed raised to the second power times the derivative of x to the third. All right. Now let's see if we can simplify this a little bit. So I'm going to run out of room here, so I'm going to erase this step right here. Erase this part. Now the derivative of x cubed, so let me bring this up here now. Okay, the derivative g prime x is equal to, this would be negative sine x squared plus, now the derivative of x cubed is 3x squared, this would be plus 3x squared sine, now x to the third power squared would give us x to the sixth power. This is our derivative now. So this is our derivative. So the derivative of, now if you want to, you can rearrange this. You can do 3x squared sine x to the sixth minus sine x squared. And this is it. Now the key is to break your integral up. If the upper bound and the lower bound are both variable expressions, use 0. So it'll be the variable, the lower bound to 0, and then from 0 to the upper bound. Break it apart, and you're going to do two separate integrals. Take the derivative of each, and then simplify your expression. So this is our expression here in terms of x. This would be our derivative now. Still not that hard of a problem, but you're just using the chain rule twice there as you divide the integral up into two. Now, hopefully you found these helpful. In our next video now, we're going to look at some applications of the fundamental theorem of calculus. We're going to look at the net change theorem. We're going to look at some accumulation functions. And we're going to do some velocity acceleration. So we're going to do some of those.